All right, so technical difficulties solved. We're going to get started with the afternoon lecture and exercise. And we have Dr. Aaron Geller, who is CIERA's visualization expert and has made a ton of presentations that show up in all sorts of media. I think there was one recently on the front page of CNN, this sort of thing. So, yeah.
Thanks, Brian. Yeah, I'm sorry, I was distracted by not being able to mute my audio, but hopefully this doesn't come through. My name's Aaron Geller. So just to expand a little bit on the introduction, I'm a research faculty member here at CIERA. I've worked in various different locations around Chicago, including the Adler Planetarium, and with Northwestern IT, where I'm a senior data visualization specialist, part of the data science group there. So I have a fondness for data science and astronomy, so I love that you all are here pursuing these two things. I've been at CIERA for about 14 years. I started as a postdoc and just kind of stayed. And so I am also happy to talk with all of you about that type of career path and career paths that involve data science and visualizations. But what I'm going to talk to you today is kind of building off of the presentation that Brian gave earlier, which I have titled Why, How, and When to Visualize Your Research Results, also known as whatever it says on the schedule, which is also a great title. Okay, we're going to start with why. And I want to give you a kind of anecdotal experience that I had early on, showing you a visualization, a movie that I created a long time ago as part of the, which we used at the Adler Planetarium. And this is based on some work that I did and continue to do. It's an n-body model of a star cluster, like an open star cluster, maybe 1,000 stars over many billions of years. And the stars are moving around because of gravity, and you can see them changing shapes, sizes, and colors. I guess not so much shapes because they're all spheres, over time because of stellar evolution. I'll explain one more time. And you know, as with any simulation, or most simulations at least, this came out as obviously a table, or actually many tables of lots and lots of numbers. And my motivation for creating this originally was for like talks or for communicating to the public. And when we first made this, I treated all the stars' sizes based on their actual sizes. So, you know, some scaling relation such that when they get bigger, they're actually, you know, the star itself is supposed to be getting bigger. But even more importantly, when it gets to be really, really small, like a neutron star or a white dwarf, it gets so small that you don't see it. And one of my colleagues at the Adler at the time brought this up, and he was like, well, maybe we can do something different. Let's see if this is, if I actually went to that slide. So what we decided to do is to color code the stars in terms of their final state. I think this is the one that I'm playing, sorry. And we color coded the red for neutron stars. We color coded cyan, you'll hopefully see, for white dwarfs. We even had a color coding for black holes, but I'm not sure any black holes were in this particular simulation. And we immediately saw interesting things, like look at this, 2 white dwarfs. Watch this, this is a white dwarf and a neutron star. Okay. And those are things that we wouldn't have known had I not like color coded it this way. And a very important piece I didn't mention is that this was way before I had any interest in compact objects. My research area focuses on normal stars and how they evolve, and maybe what happens when they collide. So like forming blue stragglers and things like that. I didn't at the time have much of a care for these. But obviously this is like a really cool result, and you know, with LIGO and everything, and Lisa, very active area of research. So if I had known to look for that through the text that came out from the simulation, I could have written some Python script to go through, or, you know, maybe it was IDL at the time. I could have written a script to go through and find these objects if they exist. And like, you know, in the future, I did write scripts like that, but I didn't have any, at the time, reason to look for those until visualizing it, right? So this is like a serendipitous discovery in my simulations, and a reason why you should visualize your data. We are very good at picking out visual patterns, you know, through movies and images, much more so than looking at a table of numbers. Here's another reason why. Bug checking. I don't know if this is actually a bug, but so this is Gaia data. I wrote you know, when Gaia first came out, this was like DR2. When Gaia first came out with some of their data that you could actually plot in this way, I created this, this is actually in Unity, trying to look for open clusters. So each one of these circles were open clusters here. And let me show you this one more time. This was one of my favorite ones, M67. And that region, that green is like the size that you expect the cluster to be. And look, as you're like looking along there, look at how the stars are kind of like spread out and along the path toward that cluster, like suggesting to me that some of the parallaxes, or at least the way that I converted parallaxes to distance, was incorrect, because they should probably be more compact inside the cluster instead of this spread out thing. And this, I actually will be looking at some of this later tomorrow. It still looks like this when I look at with DR3 data. I don't know what to make of that. So I broadly break this down into kind of two categories of how you might, of why you might want to visualize your data. One could be exploration of your data. So kind of what I was showing you before is exploring your data. It's for an audience of you, maybe your collaborators. You might want to make many visualizations. The message maybe isn't known at this time, but you are searching through your data, and whatever the format is not as important. Comparing that to explanation, when you might want to produce a figure, for instance, for your paper, to help others learn about your data. And in this case, you probably have, you know, one visualization per message, I guess. And the formatting could be very important to you, for instance, restricted by the journal. So this is kind of, when I enter into the data visualization space, I kind of think, am I going for an exploration process here or an explanation process? And that's going to inform how I want to do that. And sometimes there's a little bit of both, like that first that I showed you was explaining my data to the public, for instance. Here's another example of a data exploration tool that I created for my actually current research on looking at photometric binaries and star clusters. It's a website. And I'm just showing you some of these examples as like, here's just like ideas, right? Of ways that people have gone about visualizing data. So in this case, we looked at many different star clusters, and I wanted a way that we could share the data with the public a little bit more so than just putting it on Zenodo. It is on Zenodo. But, and this is, by the way, this is like a work in progress, but I wanted to show it to you. So, you know, you have a data set and you want to explore it, and this option, this website allows you to create various figures of all the different data products that we came up with through our analysis. And, you know, there are many tools kind of like this out there, and one of which, you know, is actually very similar. Has anyone heard of Glue? If you've never heard of Glue, GlueViz, you should check this out. It's kind of similar to this. It didn't quite have I actually was hoping that I could integrate Glue into this, but it didn't have that ability. So I wrote my own. This is a website, okay? But it's using many of the tools that you could use. So like these are figures made with Plotly. How many of you have heard of Plotly? Right. So these are like interactive figures that you could create, for instance, in Python. In this case, I just live on the website. I want to show you one more thing, just to get your brain kind of working here. This was a fun thing that I created kind of for fun. Used it a little bit at the Adler. But again, this is my research on star clusters. And I was interested in kind of real-time understanding how does changing the initial conditions affect the outcome, just in kind of like a global kind of sense. So I had all these different initial conditions, number of stars, initial virial ratio, so whether the cluster is collapsing or expanding, size, kind of fractal dimension, and then various different ways of visualizing the data. And I wrote this in Unity to both integrate the cluster on the GPU and visualize the cluster on the GPU at the same time. So this is like a Unity game, basically, that you can see in real time. And you can go back and change the initial conditions and see how it changes the outcome. And also see what happens when you actually change the time step, because a lot of times in your simulations, the time step is very important for energy conservation. Yeah.
I'm unfamiliar with Unity.
Oh, it's so Unity is like one of the big engine like coding platforms that people use to create like computer games. There's that. There's also like Unreal is another one. So some of you may be very familiar with this. You know, thank you. I should have clarified that. This is not something traditionally used for astronomy, but it is, you know, it has the ability to create great content and analyze data, great simulations, and visualize in real time. So I thought I'd check it out. All right, this is something that we're going to be talking about tomorrow. So I'm giving you a little bit of a preview here. And all of these are tools that like I saw a need and things that weren't really available and wanted to figure out a way to create it. So it's kind of just my attempt at solving a problem. This is created with a grad student at Northwestern. It's called Firefly. And it is a tool that is, again, a website that allows you to, in real time, look at and kind of spin around three-dimensional data sets. So their group had a group of simulations, galaxy simulations, with many millions and maybe billions of particles, and they had trouble visualizing it, just period, in real time. So we developed some website that kind of optimized a few things and allowed them to filter the data, as you're seeing there, color coded in different ways, use vectors. This you can also look at in 3D. This if this was a 3D screen, you would be able to make that become 3D. In the hopes that people would use this with their own data. And that's what we're going to kind of do a little bit tomorrow, is using this with your own data. Firefly. I was trying to think if there's something else I want to say about Firefly specifically. We can also visualize Gaia data. So one of the interesting things about Gaia is that, right, it's like really, obviously the data is amazing. This is going to be a fly through. You can kind of see I'm allowing the stars to move based on their proper motions and radial velocities. We're going to fly through a little bit. But Gaia has billions of stars. And if you want to actually plot up all of those points or fly through it, there are minimal way, like there are not many ways that you can do that. Like your computer cannot actually handle billions of points. So if you have a data set with billions of data points and you wanted to look at it, it is challenging to do that in real time. And this is going to become more and more the case as astronomy gets more and more data. And so we need tools to deal with that. Okay. All right. So those were kind of like ideas of, you know, grand ideas of like there are problems that you can solve through various visualization techniques. And I'm going to get into more practical stuff just a moment. So that was kind of like how, a bit of how, or a bit of why, sorry. And a little bit more of why is, you know, not just for your own knowledge of the data, but for sharing this with the public or sharing it with the press. And so there's some pictures on here from various press releases, a lot of pictures on here from the Adler. I think that as scientists in general, and you know, frankly, people who get money from the government to do science, it is kind of our job to share that science. But maybe more importantly than that, astronomy is a really good entrance into sciences for everybody. It's very kind of visually stunning. It is something that people can just look up in the sky and kind of see what's happening. So it's a great way to get people interested in science who might otherwise not be. And, you know, this may not be something that motivates you in science, but if it does, visualizing your data and making, you know, pretty pictures is a great way to get, you know, everybody interested in science and astronomy specifically. How many of you have seen this? Right? So this is not my research, by the way, but this is basically what I am most well known for, I think, in astronomy. So this is a plot of LIGO discoveries over time. So each one of these is a LIGO or LIGO, Virgo, and Cagra data put together, merging black holes, the blue ones, and then you have electromagnetic sources down here. And you know, this was born out of an idea in CIERA and through the LIGO collaboration to create some online interactive. So this is actually an interactive thing that you can play with online, but I created a movie of it. And like, again, I am not like part of the LIGO collaboration, but this gets shown, not this movie specifically, but like this image gets shown in so many talks that this is probably what I will be forever most known for. Not my research, but this, yeah.
You get citations like online, if you can,
No, well, I don't, I mean, there is actually a paper that was just written that includes this with all of the other LIGO public outreach things. So, you know, maybe that'll get cited. But, you know, it's been fun, just like people sending email, like, can I use this in my textbook? And I'm like, sure, you know, that's what we made it. And then the actually most fun one was someone sent an email. They had like some trivia competition. This was like an astronomy group. And they wanted to put it on their like sweatshirts. So they like created sweatshirts with this on the back. It's kind of cute, you know? So that's been pretty fun, to be honest with you. All right, so many reasons why you might want to visualize your data. But how do you do it? And this is not meant to be a comprehensive list, but it is kind of meant to like be, wow, there's too many options out there. Okay. You may not use all, I hope you do not use all these options. But this is like a handful of the many options that people have used for, and myself included, for data visualization. I imagine that you all will be focusing on the Python related things. You know, the Seaborn and the Matplotlib or the Bouquet. You should also realize that, like, and this was something I learned that as part of my job in IT, a significant portion of scientists use R and ggplot. And we in astronomy, we just kind of like sidestep that whole thing. We prefer Python, I suppose. But this is a very rich, R in general has a very rich ecosystem of different plots, different, you know, even like pre-built in types of figures that you can make, and data analysis procedures, and obviously statistics. That's what it's most known. But I imagine that you all will be focusing more on Matplotlib, maybe Plotly, and the other stuff that plug in. If any of these look interesting to you and you want to ask me about them later, happy to talk about them. Okay, let's talk about some more practical stuff. I have a list of, hopefully, suggestions. And then we're going to go into some in a little bit more detail of how you should visualize your data. And some of this actually comes from Adam and Brian and some others where we've kind of, you know, mushed together other people's suggestions along with my own. I imagine this is also something that Brian talked about earlier today. And so it should be a theme. Think about storytelling. This is how we as people communicate. We tell stories, right? And so that's what your visualization should do. It should tell a story. And that's something that can engage other people in the process of understanding your data. I'll talk more about that as we're going through. So the next are gonna be like some cute kind of sayings, okay? There's this concept of the data to ink ratio. So I'm actually gonna have a nice little animation afterwards. It's harping or really digging into this, but the point is that don't put extraneous material into your plots. Pull it back, let the data do the talking. Ask yourself the question, is this thing in my plot actually necessary for the story I want to tell? Then ensure visual quality. And a question you could ask, is this geometry telling the truth? There's a very egregious error that you can do, for instance, using Excel. So I often give like workshops to people who are heavy Excel users. And you could make, for instance, a pie chart. I'm sure you all know what a pie chart is. And you could make this in 3D. And you could also make this in 3D and rotate it. I'll show you an example of this later on. But once you do that, the geometry is lying to you because now you have perspective involved. And so things that are closer to you are bigger than things that are further away from you. And the pie chart relies on areas. And so if you mess with the perspective, the areas are lying to you. I suspect none of you will fall into that trap, but nonetheless, ensure visual quality. Okay, reduce the clutter. Is it necessary to have 20 different colors in your figure or 10 different symbol sizes? Or could you identify one region of the plot or one particular data set that is the story you're trying to tell and highlight that in some way, leaving the rest kind of in a background? Increase the efficiency. Is it too hard or is it too time consuming for the reader to look at this figure? You really want the person to look at your figure and immediately get to the answer or get to the story that you're trying to tell. You don't want them to have to look over here, look at the legend, read the figure caption, look back with that knowledge, see something new, and so forth. You want them to get the story right away. So the quicker that you can get them to that, the better. And a good way that you can get at this is to give your figure to somebody else to look at, get feedback on it. You know your data really well. So to you, it might be totally obvious what's in there. But once you give it to somebody else, they may not see it the same way that you see it, having looked at it, you having looked at it for weeks at a time. Okay, and always consider accessibility. Is it safe for people with color vision deficiency to see? Can they, also known as color blindness, can they see all the colors? Is the font large enough? Oftentimes, if you just take the default font, like from Matplotlib, the answer is no, it's not large enough. So you want to increase. And then last on this page, organize and guide. Is there a way you could regroup your data in such a way that it tells the story better? Could you add some helpful text to help guide people along? Okay, I'm going to expand on these and add more, but first, look at this. This is an animation that I was alluding to before that goes through how to, in this case, improve the data to ink ratio, but really, pare back, remove all the extraneous things so that you tell a clear story and you're not distracted by all this extra garbage. And it's going through all the things that it's doing. Start off with something horribly distracting and ugly, and coming to something that's very streamlined. And in this case, it's telling a story that, I guess, bacon, you want the person to see how bacon compares in terms of calories to the rest of these other snacks. All right, so starting with this horrible background, started with the bar chart that had some like three-dimensionality, bezels, shadow, all these different colors that weren't necessary, and even various labels and things that eventually weren't necessary for the story. I know that like in a lot of times in astronomy, we don't tend to show bar plots, but these are very easy for people to understand. See them all the time. And I kind of like it. At the end, notice how they directly label them. That's something to keep in mind too. All right. Digging a little deeper. One of your tools in your toolbox of how you can great good figures, the salience. And that is like the ability for someone to get right to the point, right, to see things very quickly. And as an example, there's a few examples on here, but let's look at this. If I was to ask you to pick out the red A's, this is something that you could do very, very quickly, I imagine. I can do this very, very quickly. Just by looking at it. If instead you were asked to pick out these black P's, I imagine that would be much harder for most people. It's very hard for me. I would have to go through letter by letter, line by line. It'd probably be helpful if I could like actually circle it so that I can remember, because once I get down here, there's a chance I forgot where the P's are up here. Right? You want your figures to be like finding the red A, not finding a black P. And it's a similar case over here, right? If I ask you to find this kind of symbol, you can pick that out because it's very different from everything else. But if I ask you to find this, that's very difficult. It's hard to find that at that specific angle. And so you have many different ways that you can do this, not all of which are going to be relevant for you. But here's a few different possibilities, different color to call it out, different shape. A lot of times in our plots, right, the default option is that you get a legend. You have multiple groups of data. Your matplotlib, you label each one, as.legend. There you go. But actually, this is not the ideal way, because in many cases, because it requires the viewer to look at the figure, look up here, look back down, and there's this kind of delay in understanding when it's much easier if you just directly label. So rather than having the legend, you put the labels at the end of each line, in this case. Then you don't have to look back and forth. You see the line and you see, oh, the red one's computer science. Here's another example, although disgusting. There's actually a lot of information here. Each one of these is a reason why a hotel chain lost guests. And the point of it is that bed bugs are the biggest reason. I put in these, by the way. This is not part of the labeling it. The design is very clean, right? Each of these, you could have made each of these into a pie chart, for instance. It's fractions of a whole. But instead, these are like stacked bar charts. There's a label here that describes the most important finding and a nice title. Colors being used pretty wisely to draw your attention. And in addition to that, although this is really what they want you to tell you, what they want you to see first, there's a lot more data that you could then look at and peruse at your, afterwards. So it's kind of like, more stuff that you could see, like for instance, oh, signs of smoking actually wasn't so bad. People just want to in the room, right? I realize that in like astronomy, we don't often, for instance, produce plots exactly like this. We don't often label things like this, but we could. But the point still stands that you want to have people see your story quickly. And it is also great if there's additional information that they can get out of that later after they get your story. Okay, another tool that you have is symbols. And Brian talked a little bit about this, and I'm going to add just one bit on here that I'll argue that open circles are typically the most flexible. I think I learned this from Adam, actually. And the reason why is that you will never overlap multiple circles to create open circles, that is, to create a new open circle. And you will never overlap open circles to hide an open circle. So like, for instance, look here. There is a circle here. And it is not there. But with closed circles, these are both the same. So there is actually a closed circle here, but you couldn't tell. Open squares have an issue, especially if you're looking at different sizes, right? Because you could overlap squares and create a small square. or overlap squares and create one big square. It's cool. Here. You have similar problems with triangles. Pluses are also great, except if you're using pluses and squares, because you could create squares. So even when you think about like what symbol are you going to use? Think about it carefully. Don't just stick with what the defaults always are. And Brian gave you some other, I skipped a few slides in here that I originally had because Brian gave you some other great information about how to choose symbols. And I also want to build a little bit on what Brian was saying about colors. We're actually pretty good in astronomy these days, I think, for the most part, in choosing colors. And a lot of sciences are not. So when I give this talk and I say, do not use the rainbow color. Many of you are probably like, oh yeah, I would never do that. But a lot of other people are like, oh, tell me why, because I use it all the time. And I will preface this by saying I have used the rainbow color map in a paper, at least one paper. But I'll tell you why. There's a few reasons why, and it's spread over multiple slides. In this case, you have the rainbow color map, and we're talking about different quantitative steps along at different sections of the color map. So down here, a step of 1 is essentially no difference in perceived color. Up here, a step of 1 is a huge difference in perceived color. So that automatically is a problem because you're not being honest with the audience. Anything that lives with here in your data, you're going to really emphasize the change between these, and anything that lives in here in your data, you're de-emphasizing. And so, how do you choose to set where that lives on your data? Okay. A little bit better, is something like a warm color map, something that has a kind of similar step. But the real test is to convert it to grayscale. To look at it in grayscale and see if it really is visually a similar step between two of the same quantitative steps. These are, as you probably know, the recommended color maps for sequential data. This is the default, right, in Matplotlib, so you're pretty safe there. It wasn't always the default. And there's a whole bunch of others that are similar in the sense that moving from left to right, in this case, you get a smooth change in grayscale, and every step is quantitatively, every same quantitative step gives you the same change. And you kind of prove it to yourself by looking at the grayscale. Oh, and by the way, I have these slides on my GitHub repo, and I can share that. I can share that on Slack. These and for tomorrow. There are a lot of other color maps that are available to you, which are not recommended. So here's the rainbow one again. Look at this converted to grayscale. You've got these kind of hot spots. Right? So data that lives, especially here, where you go from really bright to really dark, that's going to be emphasized. That change there is going to be emphasized. And you don't want to do that. That's not being truthful to the audience. So, stay away from most of these. Some of them seem to be okay. Oh, typo. In astronomy, we often have many dimensions to our data. And kind of ironically, tomorrow I'm going to be talking quite a bit about three-dimensional visualization using Firefly. But there's like very limited circumstances where three-dimensional visualization actually works. And I would say you want to limit that to a scenario where you can interactively rotate something, or you have a movie showing it. But if you're projecting that three-dimensional thing onto a flat surface, probably don't do it and do something different. And here are just two options of how you can show multi-dimensional data sets in 2 dimensions. This is one that we use very often. Many of you probably have already used it in astronomy. Corner plot or a matrix plot. There are various packages, including Seaborn, that can create plots like this. By the way, this is just a very typical kind of testing data set that people use. You may be familiar with. It's different flowers, different iris, types of iris flowers. So, right, so there's different kind of, I guess, species, and you have many different attributes, and you want to see how do they all relate to each other, right? So in this case, using color to describe the species, and then plotting them, each of the different attributes against each other in this kind of matrix plot. And in this case, there's one kind of outlier that they're highlighting. Another option are these parallel coordinate plots, which I think is less used in astronomy, but give similar information, but also show kind of like the connection between for one flower in this case across the different dimensions. So one line corresponds to one flower, whereas one of these lines is a dot in every one of these panels. And it's just connecting sepal length and width to petal length and width. And the only difference between these two is just the scale of these axes. Well, this one is scaled to the kind of min and max of the data, each individually, and this is scaled so they all go from 0 to 8. Oh, and again, there's this red one that they hide. And so that's the outlier that they're trying to draw attention to here. So I would say if you have data that is multiple dimensions, try for some 2D representation first, a slice through your data, looking at different axes. And if you need to go 3 dimensions, probably the only reason for that is that you're plotting something actually on the sky, X, Y, Z coordinates. And you want to be able to rotate it, and you want to be able to, zoom in, zoom out, things like that. There are various websites that can help you choose what type of plot you should make for your data. This is one kind of figure that I borrowed from someone. This is a great website, data2viz.com. Gives you all these different chart types based on the different data you have. So if you ever are kind of at a loss for what you how you should visualize your data, this is a good place to start. I also want to talk a little bit about artistic license. This is a painting that I made. It was one of my first visualizations of a science topic that was way back in grad school, or maybe right after I finished grad school. And this was meant to show a blue straggler star being formed by accreting material from a red giant. And what you eventually end up with is a white dwarf. So this material eventually leaves the white dwarf. Some of it gets accreted by the blue straggler to create the blue straggler itself. And you end up with a blue straggler attached to a white dwarf in a binary system. In reality, if this was, a real simulation, you would never see this white dwarf like this through here, through all this material. But we wanted to tell that story. And so, we put it in there. Okay. And I think we can do that in certain scenarios. Okay, so this was like for a press release, we had some description about it. It was, totally tried to be clear that that's not exactly what you would see on the sky. But you got to be a little careful. But I just want to put that out there, something to think about if you're ever developing press release images. This was not, you would never make something that has artistic license if it was from your data and you're doing it in Python and putting it into your paper, because you're not going to go to Photoshop and I think I should add a point here. Don't do that. Okay, that's not what I'm talking about. I'm talking about something that's, you're drawing it for a specific purpose, like this. This is another example. So this is another press release image that I made for a CIERA member here, and it's this a supernova remnant with a black hole in the middle, this amazing jet coming out of it, and then it's in a star forming region back here. This is completely made up. There's no simulation. I mean, okay, I shouldn't say completely made up. The concept came from the observations. Okay, but they didn't actually have a picture of this. And there's nothing that said this should be green and this should be purple specifically. But I thought it looked nice and it had a good visual impact. And like sometimes these types of choices you want to make so that you can have that impact on your audience. There's another example of artistic license. We also live in oh yeah, go ahead.
Question on the previous slide.
Yeah.
What kind of guide your intuition for finding that fine line between artistic license and producing something that might be visually impressive and give the audience, especially audience with science, that are the wrong idea about the science?
So I will step back as now I'm the senior data visualization specialist from IT. I'm not an astronomer. I will work with the researcher. And I will, I come up with some visual ideas that I think are nice. I will show it to the researcher and say, is this okay scientifically? Is this misleading? Right? So I go to the expert and say, this is, they make the choice. If I am the expert, yeah, it's kind of like a case-by-case basis. I think there's no like hard and fast rule to this, but you kind of hit it on the head right there where you don't want to be misleading. Like it is possible that this is what it looks like. It has some texture, you put in a certain filter in your camera and you come up with green in the background, right? It's not incredibly incorrect. It's just choices that are made for visual impact. Yeah. It's a great question. So we live in a time with rapidly growing abilities of AI, right? And including generating images. So maybe at some point we will be able to just generate our press release images through, in this case, DALL-E 3, but not yet. So like, for instance, please create, this is a prompt. And by the way, this was maybe 6 months ago or something, a year, it may have improved, but anyway. Please create an image of a cosmological volume with multiple galaxies with active star formation. And this is what it came up with. Right? I mean, maybe I could tweak this more. I have tried a lot of times to get a generated image that's like, I could just use this. And I have not found one. Like these are not physical, but they are, very detailed, and in some cases they may give you some inspiration for doing something on your own. Please create an image of a blue straggler star forming by accreting mass from a red giant star. And lots of detail. I mean, it's kind of sci-fi. Some of this is pretty cool. I mean, I don't know, this is almost like a brain. So it could, I don't know what's interesting how it had very similar color choices too. I don't know what that's all. And then the last one here, please create an image of a supernova with a gamma ray burst inside a star forming region. So like similar to the one that we did before. Some of these are actually pretty interesting. Like they do, like the gas is kind of fun, and I like some of these ideas of the rays of light coming out. But we're not there yet with generative AI. So, I don't recommend you just going there and using that for your press releases. All right, so we're almost at the end of this portion. Just want to kind of pull everything together. Talked about how and why. So why, various reasons: scientific discovery, public engagement, data exploration, explanation, bug checking. You have a lot of tools for how you can do it, focusing on storytelling and making sure that that carries through to all these different tools. I didn't actually specifically say when, but hopefully that has been kind of implicit throughout my talk and Brian's talk, really early and often. And both of these are important, right? So don't go too far in your data analysis or data collection without visualizing it, because you may catch some mistakes. You may make a discovery that then puts you on that path. And then do this often. Like you're going to, first of all, for every plot that you make, hopefully you make multiple drafts. You make the first one, maybe you want to tweak it and you improve it. but also along the way, you know, if your data changes, remake that plot and so forth. And then I have two cents to add to this. I think that interactivity can really enhance many of the whys that I had above. And so in those examples that I gave before, you saw that many of those were interactive. Maybe all of them. Most of them are interactive. And I think if you can allow the user to explore, to have the opportunity to explore the data, or you yourself to explore the data in an interactive way, you'll get more out of it. And we are really in dire need of innovative strategies for visualizing large data sets. So like I said, you know, when we're talking about Gaia data from the LSST survey, and the Rubin telescope, it is really going to be a challenge, especially if you want to do this interactively. Just like computers are not built to visualize billions of points interactively at the same time. That's just where we are. So we need strategies for doing this. You know, and maybe that's something you all want to work on. Okay, so I want to take questions, and we can, I think, take a little bit of a break also maybe before we get into the next section. I have a Python, so the next section is going to be like a problem exercise. I'm going to have a little guided thing for you first, Python demo, and then I'll let you all work for a little bit, and we'll have kind of like a discussion section, kind of probably similar to what Brian did with the drawing, but this time using code. But I want to open you up to questions for a little bit. There you go.
So I'm assuming that you often see people come to you with like data visualization, or you see data visualization, like existing astronomers talks and papers. What do you think is the biggest pitfall that astronomers currently fall in? Creating plots?
Trying to do too much with one plot. I think, and I have fallen into this trap myself too. So I'll give you that, and I'll give you a secondary too. Trying to do too much in one plot, meaning that you just have this super complicated figure, and maybe it gives so much great information, but it just takes forever for anybody to understand, and they have to read through it like a 20-sentence figure caption to like get through what all these symbols are. I think that's very common. And unfortunately, it's like we just kind of accept that as a given, and we're willing to deal with that. We do that all the time. But I think that's a problem. The other one that I will say is that, and this is less of a problem, but you go through your data analysis and you've made these many beautiful figures along the way, and then you go to write the paper, and the paper has a particular narrative that requires some number of figures. But you made this beautiful figure and you really want to put it into the paper, and so you do. But it doesn't, it's not needed in the paper. And I think that's another problem. We don't need that extra. Yeah.
Kind of organize the thought a little bit,
No problem.
but with some of the visualizations, lots of different data points, and then the black hole one earlier. From your experience working with different softwares and working with like data which may be smaller and smaller sets versus big ones, how much do you find yourself working on the balance between like tweaking your data to actually like visualize it the way that you want to, like to create a particular pattern, like with the black hole image, or just like trying to get it so that the program is doing what it can, and then you're just playing with it? Because I tend to get into the habit where I'm like, if I add this column, I can make it easier to sort it this way, and I can do this one other thing. But how much of that actually makes it into the final product is it's so much.
No, that's a great question. I think there's, yeah, so you basically brought up kind of the two different philosophies. So going back to that black hole one, the goal there was that I would be able to ingest data that came directly from LIGO. So I didn't actually like manipulate the data initially. Just give me that data, I will put it in and do all the manipulation through code.
Yeah.
And I tend to work that way Most often, it offers a few different advantages in the sense that like you don't have to like pre-process the data to get it into your figure. But also, you can see everything that's happening to the data from the point of getting it to going through, as long as you're willing to look through the code. Adding an extra column though, that doesn't seem like too big of a problem to, do that to sort by. So, you can imagine a couple different steps. You could imagine a data cleaning or processing step, and then a data visualization step, where that data cleaning, for instance, adds that extra column, sorts the data and however you want. And then the visualizing is just creating the plot. So you could separate those two, or you can put them together. And I think as long as it's well documented and it's reproducible, then it's okay. The reproducibility is the really important part.
Really question over there. What do you think? I mean, this is going to be subjective, but visualization is a time-taking process. So, at what point do you, consider that I have invested enough time into this?
Yeah.
This does not seem like it's going to get any
Yeah.
further, and kind of decide.
Yeah.
Where your threshold is for the level of interactability that you want with your data sets or something like that.
Yeah, another great question. For me personally, it has often come down to like, what do I want to spend my time on? And it just so happened that when not just so happened, I should say, all through my life, I have been very interested in the visual side of things. So, I went into college as a double major in physics and art, like painting. I came out with an art minor, and I've carried that art with me. And now, through things like this. So I have always wanted to kind of invest my time. So like I was telling some of the people at lunch that I spent a summer in Australia working with Jared Hurley, who's an astronomer at Swinburne, and he runs N-body star cluster models. And actually one of those, the first visualization I showed was of a model that I created while I was working. But anyway, when I was there, I was trying to figure out how to make these movies. And, at night, I was just there writing code, running it to produce some movie, looking at the movie the next day, because, this was very inefficient what I was doing at the time, and realizing I needed to tweak something. And it took like a month for me to get that first movie. And some people might say that was too much time, right? And had I actually reached out to someone like an expert, they probably would have said, well, you could do it this way. But I actually think in the end, just spending that time for me was very helpful, just learning about the way of doing it. So you got to balance, your interests versus your advisor's pressures and your own self-imposed pressures to get the job done. So what is your job? What are you getting paid to do? And like, yeah, when is it good enough for this purpose? And who decides that? It could be your advisor. This is good enough. You move on. Yeah, so that's a long-winded way of saying I don't have a cut and dry answer. But it's something to think about. Yeah.
For each individual you make, especially when other people come to you with their work and saying that you help me create a visual of it, do you start from scratch and try to come up with a unique idea, or do you find yourself relying on visuals in the past? How can I modify that?
Yeah, if I have something that I've done in the past that is that I can adapt to this new purpose, yeah, I'm going to start there. I want to save. I don't want to reinvent the wheel if I can. And I'm also going to look online to see what other people have done, so that again, I'm not reinventing the wheel and trying to make the most efficient use of time to get back to that. Yeah. Over the years, I've developed a lot of different things that I can then use later for something else. But at the start, obviously, I had to create all of that.
This is just something that kind of weighs on me, but in terms of these more complicated 3D visualizations, how do you consider the amount of computational power it might require, and the trade-off between how useful that might be to you versus is it just using too many resources?
Yeah. No, I think that that's actually like, the one that I showed in Unity. I mean, there's no reason, there was no reason that other people, or that I should really do that. On a regular basis. I think it's like an interesting thing to kind of show, and it was an interesting learning experience. But yeah, I do think about that, and especially if you're making something that you expect someone else to run on their computer. It's like all these websites, it's something that someone else is actually, their computer is running it, so you have to make it such that realistically it could work on other people's computers. And like, we'll see tomorrow if Firefly works on your computers. It might not, we'll see. Yeah, definitely worth consideration. And also, like, if we're talking about image generation with Dolly, those use a lot of energy. And like, and clearly those aren't worth the time to generate, other than for like a laugh in this type of presentation. So like, should we be doing that? I don't know. Carbon footprint.
So let's maybe take a 2 or 3 minute bio break before we get into the Python demo. Good.
Thanks, everybody.